Fine, thank you.
Good. Okay, well, during this class, this is going to be our agenda. First of all, we have the basic structure of a computer, just the basic functions. Afterwards, we have the hardware and von Neumann architectures, the main features and differences, and the definition of features and example with a big microcontroller. Okay? Well, that's for the agenda of today. Not only that, we'll have an intended learning outcomes, and this is what I expect you to provide after this class. Set a clear idea of the computer basic functions. I mean, that you can have the comprehension of what are the idea of a basic computer functions is. We have also the understanding, and you can be able to identify the differences between computer architectures, I mean the hardware and von Neumann, right? And at last, describe the behavior and the importance of the algo with a computer system. Okay, what's a computer for you guys? What's your understanding so far?
It's like an electronic device that processes data.
An electronic device that processes data. What else?
Well, anything nowadays, I mean, even a microchip can be a computer, like a smartwatch, a computer inside. Even, like, I saw some clothes that have a big piece of computer inside to process any sensor or something like that.
All right. Well, that's in fact true. Part of the computer functions is that we have an input, a CPU, a central process unit, and the output through ports. Okay? These are our output peripherals. Within the CPU, we'll have a memory unit, a control unit, and an arithmetic and logic unit. Okay? And this is what we'll see in the next slides. Okay, guys?
Yes.
Well, the next slide. The basic functions of a computer. First of all, as we said, we take an input. Where do we take an input from a computer? Screen?
Well, I mean, I guess use a keyboard for input.
Mouse. You get the keyboard from users, okay? From the real life. I mean, the computer has its ways to process the information, but it is not information that comes itself from the computer, okay? It comes from outside. And this is why it is involved. Entering data and instructions, that's the first operation. Second one, store data. Sorry, data. Okay, saving data and instructions that they can be available for processing when we require. Okay? If we don't have data inside a computer, there is nothing that we can expect. Okay? The third, data processing. Performing arithmetic and logical operations and data in order to convert them into useful information. Okay? This is involved. Useful information. Okay? Remember, we'll have involved all the key points that we need to remember. Right? And then last, the output information. The process of producing useful information of the results for the user. I mean, the computer, as you stated, it's an electronic device that allows us to process and store data and transform it into something that we need. Alright? Is it clear so far?
Yeah.
Okay. I had some technical issues with the presenter. Okay, next topic. von Neumann and Harvard architectures. I think, guys, you may recall this topic, and the main idea is there. Architectures can be classified by how they use memory. And I state once again, this is not the only way that we classify computers, okay? This classification is how they use the memory, how they organize the memory, all right? Okay, for the von Neumann architecture, what can you think, what can you guess about this diagram? Do you see any key point about the data, how the memory is located?
From the CPU and all the work.
Okay, where is the memory? Here. But you remember, memory is not just once. We have two memories, right? Which are them?
Dynamic and static. Or
This is a classification for.
like run, read only memory.
Okay.
Random access memory and read only memory.
You're almost there.
Volatile? Not volatile? I think you had something to do with that.
Do you remember, guys, when we want to attempt to a variable? Where is a variable stored?
In the RAM.
RAM, okay? And that's main memory, correct? And the other memory, the other type of memory is? Sorry, first?
Program.
Secondary.
Program memory and secondary memory, yeah? You remember the program memory is where we store what? Instructions or code, right?
Yes.
Okay. What can you see here? Both memories
At the same place.
are located in the same place.
CPU.
And we have bidirectional buses. Okay? And the other devices, the input and the output devices, which is logical inside a computer, right? Okay, moving forward. Harvard architecture. Whatever you see, guys, what's the first impression that you get from this picture?
That the memories are not stored in one place, they're separated.
Correct? It's a good point. What else you see?
Every part of the CPU is connected directly to the CPU in two directions.
Correct? And the CPU meets its purpose, right? It's central process unit, okay? Well, part of the text, separated memories. We are able to run a program and access data independently, okay? Besides the von Neumann architecture. And another feature, it could be the data code is more complex and expensive, you know, because we have split the memory. So far so good?
Yeah.
Cool. All right, moving forward. Next topic. What's the EU? I don't know. You know, guys, arithmetic, logic unit. And what's the main idea?
Processing data.
Process data.
Like performing arithmetic
Arithmetic
operations.
operations.
Okay. And what is an arithmetic operation?
Like,
Like addition, subtraction,
Okay, one by one. Okay, you have enough participation, but it's cool.
Oh,
That's for maybe a later on.
sure.
Addition and multiply,
Addition, subtraction.
divide.
If I tell you that I have an OR operation, is it an arithmetic or logical operation?
logical.
Logical, right? What are types of logical operations you know, guys?
Exclusive or.
Exclusive OR and OR else? Not. And
Nor.
you remember shifting bits? Okay, if you don't recall, we'll talk about that later. No problem. Okay. Well, for the ALU we have two operands. What does this N mean?
A number.
A number? You sure?
Variant. Just operand.
No. Because here we have the operand 1, operand 2. But if you see, on the result we have also the same N. You see this line crossing?
I think that's the number of bits.
Exactly. It's the bus length. Remember, we'll have for the big microcontroller that we will use, it's how many bits?
8 bits.
8 bits length, right? Okay. So, what it means? It means that our inputs will come a bunch of 8 bits, okay? Because this is the length of our bus. Alright? Alright, well, basically we have two operands, results, opcode, and status. What is the opcode?
It's what decides which operation will be applied to the operands.
Correct. Is it clear for you guys? Okay. I see many faces of what? Let's keep on with the topic. Operand A and operand B, and the result is a Y. This is the diagram of a basic ALU. What does it do? Opcode between two operands, perform the operation inside this structure, and the output will come on this register. Okay? And not only that, we'll have an status. See the arrow? It's an output, correct? What does it mean that we have another output besides the result?
Well, I mean, I think that can be used for stuff like a zero flag, which tells you if the result of an operation is zero. Basically, just tells you the status of the operation that you're performing.
Yeah, if you have a sync, to make that process less work. I mean, like you don't have a -1 because not another processors can give that information at all. -1, I don't think it exists in a processor like that.
Exactly. This is not the way that computers process that data, correct?
Yeah.
So, the status is something that let us know what happened here into. For example, you remember when you had your additions, you used to have a carry. What did you do with that carry?
Like for the addition algorithm, we used it to like.
You use it for adding, right?
Yeah, for adding.
Or a subtraction, the opposite, correct? And that's a flag. Status is an array of flags that will let us know what happened here through the operation that we chose before. Correct? Okay, this is how it looks like. If you can see, maybe how many of these flags you remember, guys?
Zero flag.
Zero?
Carry.
Carry flag. Carry flag.
Negative.
You almost identify all of them, correct? Good. So, carry flag will let us know the carry, if there was a carry output within the operation. Digital carry, this is it is also called in other microcontrollers like half carry. What does it mean? That it performs a 4 bits operation. Instead of having 8 bits in addition, let's say, we have 4 bits. And in the 5th bit, what do you think, guys, this flag will do?
0?
It will go to 1. It would rise to 1. Set. Okay? Well, negative flag as what do you remember? This already. Gabriel? Gabriel, okay, as Gabriel stated before, this is not the way that a computer proceeds with the negative number, okay? We just raise the flag, we'll check it in our algorithm, and add it if it is the case, if we have a negative response. So far so good, guys? Okay, because that's your turn now. Types of operations, as we stated before, we have arithmetic and logical and bitwise operations. Add, subtract, to complement. What does this symbol mean? You remember?
Not?
Exactly. That you negate the input. Increment, decrement, and this is also called as
Minus or plus?
yeah, in a high level programming, right? What else? Logic and bitwise operations and or exclusive or one's complement and then bit shifting. You remember how we set the bit shifting in a high level programming?
Oh,
You remember these operators? Shifting, how many?
I thought it was called displacement.
Displacement, yeah.
Okay.
But it's a bitwise operation. Why? Because remember, in a high level programming, you used to have a whole variable, meaning in a decimal, right? In a decimal system. But the computer does not understand the decimal. It just understands binary. Okay? Alright. Well, 1, 2, 3, 4, 5. Who wants to participate?
I'll do it.
I'll take it.
Choose your preferred.
You are the brain.
Oh no! Who wants to go next? Okay. The next one, I think I need,
Which one?
I need to choose.
Wherever you want it. Which one
Jewish?
Whatever you want.
Whatever you prefer.
I don't know. I don't know.
What is this? These two are.
You remember this operator, guys?
Or.
Exactly. It's an OR.
Sure. I tried.
The number one is XOR?
Yep, the last one is the
XOR. This is
it.
OR.
Go ahead.
I don't remember.
For the rest, if you guys want to take a participation, you can do it on your notebook,
You know what?
and I can take it in account. Done?
Yeah.
Which one did you do? The addition? Ready?
Okay, you got the algorithm.
It doesn't.
What about the blue one?
What about the blue one?
Yeah. Is it right?
Which operation is this?
And
0 and 1? 1 and 1? 0, 1, 0, 1 and 1? 1. Okay?
It's correct. Is.
Okay, and or.
Like an inverter or
Yeah?
you have the opposite.
Oh, okay.
You have the opposite result.
Okay.
Inverter or.
In assembly. Remember, you don't need a compiler. You got your own compiler in your head.
We apply we have any another macros and all the.
Forget about the macros, right?
Okay.
Just state the basic code. And this is what I
oh, use for P, right?
Sorry?
I will use for P.
Port B. For B is not necessary. Why? Because I'm just going to another part of the code.
Use the main. Just do the main.
What?
Just do the main.
Ah,
Forget anything else.
the name.
What do we do first to declare a variable in assembler?
The name of the variable, we use the EQU, and then the value.
Exactly, that's a reserved word. It's equal. Okay?
Zero?
Key is defined bar variable 1, yeah, on the address 01. Correct? What's the next?
I jump.
I need to check if this variable meets this condition. How can we do? You recall that we have an XOR operation? Listen, this is what you do. For example, 7 in decimal. How can we transform it into binary?
3 ones.
8 bits?
4 bits length. Let's do it this way. Okay? So, without applying an XOR, we need to define what? The same value. Why? Because if this is the variable, and this is our constant, what will be the result here? 0, 0, all zeros, right?
Only if it's the same value.
Exactly. And what happened with these zeros? What happened to our status register?
0, 0, and 0 flat.
0 flag turns into?
1.
Okay? Now, let's move the value from a variable to our working register. You recall this instruction?
Move.
No, it's move 5.
Let's move 5, exactly.
Yes.
No. How many moves do we have on the PIC microcontroller? Move LW, move WF, and
That is the second one instruction.
move F.
Just move 5?
Yeah, move 5. From 5 to
Oh, yeah, right.
our working register.
So,
Yeah, that was fine. That was fine.
okay.
Exactly. And what is missing?
The workplace?
The workplace. Exactly. Or working register. What's next? On that instruction, we have loaded the variable 1 into working register. Correct. Now, what's next?
You have to look at constant, right? You need a constant as well.
Clear the constant, right? What do we need for that?
Define it. We have to define it.
Define it. You can define it at the top. How?
It doesn't have to be 7 as well.
It has to be.
Back. No, let's take that right. We didn't check this one, right? Oh, the X, the D5, D6, and D7. I mean, I don't know
What does it mean?
Yeah.
Good question. Does someone know the answer?
Yeah. Well,
What do you think, guys, is our result?
because if you want to use them in the future, I guess.
I think I have a
So,
number,
you-
like the result of the number is too big. You can use it like the number is over wrong. No, right. Forget.
At was a good question, and you know this is out of the topic. But these bits, I don't know if you recall, RP0 and RP1. You recall? They are flags that tell us the
Is this one?
index of the RAM memory. You recall?
Instruction.
Yeah.
So these bits are used for these two flags, and we can change them every time we want on the code. Okay? Okay. What else?
Is right here.
Any other question? Thank you.
Sorry.